Okay, so this is chapter 7, where we're going to talk about chemical reactions, um, and then look at how we use chemical reactions to do some calculations. So we're going to start to look at how we write out chemical reactions and how we know that a chemical reaction is going to be occurring in this chapter. We're going to see a chemical change as a result of any chemical reaction that happens. And remember that a chemical change is when we start out with one substance, and over the course of the reaction that's happening, it's going to get converted into another substance, or maybe more than one substance. Okay. So we want to be able to figure out when a chemical change is occurring. So we're going to notice that there are some observations that we can make that sort of go along with the chemical reaction happening. All right. So we'll see some maybe bubbles forming. We'll see a color change. We might see the production of a solid, or we might see that some heat is either produced or absorbed. So we'll see a change in temperature. Okay. These are just some visual examples of what we're talking about with each of these changes. So this is like a change in color when we see the rusting of some iron nails. You see some bubbling of gas. We're seeing a solid form here in this reaction when we have two aqueous solutions that are mixed together. And when we have something burning, okay, that's going to be a chemical reaction. We see the formation of heat here. Okay, so let's look at how we write out chemical equations. This is an example of carbon and oxygen um, producing our carbon dioxide. We're going to talk about what this delta symbol means as well. So whenever you're writing out a chemical reaction, you're going to notice a few different parts of that reaction that repeat no matter what the reaction is. So you're going to have your reactants, which is what you start with on your left side. And you're going to have your products, which is what you end with on your right side. And there's going to be an arrow that separates them. Okay. So you'll have your reactants on the left. So like here we have reactant plus reactant. Then you have the arrow. So this is going to represent the switch that happens. And then you're going to have your products on the right side. All right. If you have a delta sign above your arrow, that means that you have heat used to start your reaction. You could have one reactant on one side and one product on the other side. You could have one reactant and then two products. Uh, there's not a rule to like the number of reactants and products that you start with and end with. That's not the thing that has to match in your chemical reactions. We'll talk about what needs to match in a minute. But you'll see that when there's more than one reactant or product, they're going to be separated by a plus sign. Okay. And then we're going to follow each of the formulas of our compounds in our reaction by the physical state that they're in. So we're going to have an S for solids, an L for liquids, a G for gases. And then when something is dissolved in water, that's going to be called aqueous, and that's going to get an AQ next to it. Okay, this is our summary of our different symbols that we're going to use to write out our reactions. You only need to use the triangle is called a delta symbol. You only need to use that delta symbol when your reactants are heated for the reaction to occur. Now, what does need to be balanced, or what does need to equal out when you write out a chemical reaction, are going to be the number of atoms of each element on both sides of the reaction. Okay. They don't have to be present in the same form, but they have to be present. So if you start out, for example, with 4 hydrogen atoms and 2 oxygen atoms on your reactant side, then on your product side, you have to have the same number of hydrogen atoms and the same number of oxygen atoms. All right. So the number of atoms on your reactant side has to equal the number of atoms on your product side for any element that's in your chemical reaction. So let's look at these two examples and just We're going to count the number of atoms on both sides of the reactions here. So we're really just going to look and visualize how we count the atoms in a chemical reaction for this step. Okay. It sounds straightforward, and it is once you know how to read the chemical reactions. But when it's still a new thing, then you have to like make sure that you're just looking at each step the right way. Okay, so if this is our reaction, what we want to remember is that whenever we have a subscript, the subscript is going to apply to the thing that it's directly attached to. Okay, so our 4 tells us we have 4 phosphorus here. Our 2 tells us we have 2 bromine atoms. And our 3 tells us we have 3 bromine atoms. Okay, when you have a coefficient in the front, that's going to apply to the whole substance that the coefficient is in front of. All right, so that 6 tells us that we have 6 of these things. And each BR2, now we kind of know what our like our Lewis structures look like, right? So if we wanted to visualize a BR2, we could visualize it like this. So that's saying that we have 6 of these things. So each BR2 has 2 bromine atoms, and we've got 6 of those. 1, 2, 3, 4, 5, 6. So how many bromine atoms am I going to have on my left side? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, we got 12 of those total. I'm going to have 4 phosphorus atoms total. All right. Now, if I go on my product side, my compound is PBr3. So I'm going to have a phosphorus, and I'm going to have 3 bromines attached, and I'm going to have 4 of these. Okay. And you're not going to have to draw it out every time. I'm just drawing it out now so that we can get a visualization of it. But when we do draw it out, we can count up all of our atoms. So for our phosphorus, we have 1, 2, 3, 4. Okay, so we have 4 phosphorus total, which matches what we have on our reactant side. And for our bromine, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And that also matches what we have on our reactant side. Now, without drawing it out, another way that we could do this is we can say, all right, I've got 4 PBr3. So I'm going to do 4 times the 1 phosphorus in my molecule. And then I'm going to do 4 times the 3 bromines I have in my molecule. And that also shows me that I'm going to have 4 phosphorus and 12 bromines on this product side. Okay. So let's try that method with our second example. All right. So now we're going to use our coefficients and our subscripts to help us count. So the 2 out in front tells us that we have two aluminums. Okay, I'm going to make a list of the elements on each side. I've got aluminum, I've got iron, and I've got oxygen on each side. So I've got two aluminums. My subscript here tells me that I have two irons, and my subscript here tells me I have three oxygens. On my product side, my coefficient tells me I've got two irons. My subscript tells me I have two aluminums, and my subscript tells me I have three oxygens. Okay, and I can see that these numbers are balanced out. So that's how we're going to count the atoms that are in our reactions. And when we write out our chemical reactions, we're going to want to make sure that all of our atoms are balanced. So we're going to talk through the steps to use to balance our reactions. We'll go through it by example, but we'll talk through these steps and then I'll show you how to use them. So we're going to look at this reaction here, write a balanced equation for the reaction between solid cobalt 3 oxide and solid carbon to produce solid cobalt and carbon dioxide gas. When you're reading these reactions, you have to separate the reactants and products as you read them, okay? So as you read this, they're starting by telling you that the reaction is going to be between solid cobalt 3 oxide and solid carbon. So that's what the reaction is between. That means that these two things are going to be mixing together on the reactant side. Okay. And when you see the words to produce, you won't always see, like, they won't always be written the same exact way. But in this case, that phrase to produce, that's telling us that this is where our arrow is going to go. So everything that's listed after to produce is going to represent products in our reaction. And the products are going to be solid cobalt and carbon dioxide gas. Okay. So the first two things that were listed in this case are our reactants. Then we'll have our arrow, and then we'll have our products. Okay. And this is important because the first step that you're going to take when you write out a chemical equation is you're going to write that, we'll call it like a skeletal reaction, meaning that it won't necessarily be balanced, but you're going to write down the chemical formulas of all of the components of your reaction. So whatever reactants and products that they list in the question, we're going to write out the formulas for each of those things. Okay. And then we're going to work on balancing them. And I'll talk you through the rest of these steps when we start on that. Okay. But you'll be able to come back to this slide and you'll be able to use it as reference when you're balancing your own reactions. So I would say that the first thing that we want to do is we want to start with, I'm going to write out the names here, which you don't necessarily have to do. But I'm going to write out the names so that we can look at how we write the formulas. Okay. So we have solid cobalt 3 oxide. This is why it was so important for us to understand how to name things, right? Why we spent so much time doing that. Okay, so solid cobalt 3 oxide plus solid carbon, and it's going to produce solid cobalt and carbon dioxide gas. Okay. All right, so let's stop sharing that screen so that we can look at the names for these things here. So when we look at the first name, solid cobalt 3 oxide, we're going to recognize that they've given us the name and the charge of a metal, right? So this is going to be cobalt with a positive 3 charge attached to oxygen, which has a negative 2 charge. So the formula for this right? I want my charges to balance. So I'm going to need 2 cobalts and 3 oxygens for this formula. And I'll end up with CO2, O3, and then I'll put an S next to it because it's solid. And then we have solid carbon. Easy enough. That's just carbon with an S next to it for solid. It's going to produce solid cobalt. And carbon dioxide gas. So this is going to be a molecular compound. That's why it's named with a prefix. So we're going to have 1 carbon and 2 oxygens, and it's going to be in the gas form. Okay. That's your first step. Write out that skeletal equation. And then what we're going to do is we're going to draw a line. And I like to split the reaction in half, and I use my arrow as the dividing line. And I'm going to list the elements that are present on both sides of the reaction. So we've got cobalt, we've got oxygen, and we've got carbon present on both sides of the reaction. And now I'm going to count the atoms that are currently in my reaction. I know that they're not balanced yet, but I'm going to count how many are on each side so I know what I have to do to balance them. So I've got 2 cobalts here. I've got 3 oxygens. I've got 1 carbon. Now my product side, I have 1 cobalt. I have 1 carbon, and I have 2 oxygens. All right. Step number 3 on that list of rules that we mentioned. Step number 3 and number 4 kind of go together because they tell you which thing to start with. When you're looking at this, you are going to balance your compounds first, and you're going to save your free elements for last. Your free elements are things that aren't attached to anything else. So in this reaction, the only one of these elements that are part of a compound on both sides of the reaction is our oxygen, right? Our oxygen is part of a compound here, and it's part of a compound here. So we're going to balance our oxygen first, and then we're going to balance the carbon and the cobalt second, because any change we make to the carbon and the cobalt, we might have to make more changes to balance the oxygen. So if we get the oxygen out of the way, then it'll be easier at the end to balance the free elements that are left over. Okay. So if I have 2 oxygens on my reactant side, or sorry, 3 oxygens on my reactant side, and I have 2 oxygens on my product side, I'm going to look for the lowest common multiple between them. We know that that's 6. So I know that to get the same number of oxygens on both sides, I'm going to have to multiply my number of oxygens by 2 on my reactant side, so that I end up with 6. And I'm going to have to multiply the number of oxygens on my product side by 3. So I end up with 6. Okay. This multiplier that I'm using, I'm going to take that multiplier and I'm going to put it as the coefficient in front of my compound that contains the oxygen. Okay. So I'm going to put a 2 out in front of my CO2O3, because now 2 times 3 oxygens equals 6 oxygens. All right. When I put that 2 out in front, though, I'm also going to change the number of cobalts I have. So now instead of just having 2 cobalts, I'm going to have 2 times 2. I'm going to have 4 cobalts. Okay. Go back over to our product side and see what's happening over here. I know I want to multiply my oxygen by 3. So I'm going to take that multiplier and I'm going to use it as the coefficient in front of my compound that contains oxygen. So now I'm going to take that 3, multiply it by my 2 oxygens. Now I have 6 oxygens on that side. But that 3 is also going to multiply the number of carbons I have. So I've got 1 carbon here. 3 times 1 means I have 3 carbons now. Okay. But now when I look to balance my cobalts, I've got 4 cobalts on my reactant side. I have 1 cobalt on my product side. I can just put the number 4 in front of my cobalt because it's by itself. Now I have 4 cobalts on both sides. If I come down here to my carbons, I've got 3 on my product side, 1 on my reactant side. So I could put a 3 in front of that carbon that's by itself. And now I have 3 carbons on both sides. And now I can check and I see like all my numbers match. And that's how I know that my reaction's balanced. Okay. So we've got a few to practice here. The next one tells us to write an equation for the formation of Al2S3 from its constituent elements. Let me pause real quick and I'll write the question out here. Okay, so here's a reaction that they've written out. Write an equation for the formation of the Al2S3 from its constituent elements. This means the elements that it's formed from. Okay. Al2S3 is going to be formed from aluminum and sulfur. So we could start out by writing that skeletal reaction that we talked about. We've got aluminum plus sulfur, and it makes Al2S3. We know that our aluminum and our sulfur are likely going to be solids here. If they don't tell you the physical state in the question and you're just trying to balance the reaction, it's okay if you're balancing to leave that information out sometimes. If it's an important part of the reaction, then it's usually described within the reaction itself. Okay. And what we really want to focus on here is figuring out how to balance the atoms on each side. So for this one, we write out our skeletal reaction, we get that finished. And this one's, it's a little bit easier than the last one that we did. We have aluminum and sulfur on both sides. On our reactant side, there's 1 of each. On our product side, we have 2 aluminums and we have 3 sulfurs. And so it's very easy to see where our fixes are going to go, right? We make those changes and now the atoms on both sides match up. The next example that they describe for us says to balance the chemical equation when solid Fe3O4 reacts with hydrogen gas. So it's going to be reacting with hydrogen gas to produce, so that's where our arrow is going to go, solid iron and water. All right. So our first step is going to be to put everything in terms of chemical symbols. Okay. They gave us the Fe3O4, which was nice. We didn't have to, write out the formula from a name. So we're going to write out Fe3O4 and we'll put the S next to it. Hydrogen gas. Remember that hydrogen gas is one of our diatomic elements. So it's not going to be hydrogen on its own. That's when hydrogen forms that covalent bond with another hydrogen. So the formula for that is going to be H2. And then we'll put the gas symbol next to it. And it's going to produce solid iron and water, which we know is a liquid. Okay. So now we'll draw our little chart. we have iron, we have oxygen, and we have hydrogen on both sides. We've got 3 irons, 4 oxygens, and 2 hydrogens. On our product side, we have 1 iron, we have 2 hydrogens, and we have 1 oxygen. And again, when you look at this reaction, we see iron by itself in one spot, and we see hydrogen by itself in one spot. But the oxygen is part of a compound on both sides. So we're going to start by balancing out that oxygen. Okay. We have 4 oxygens here. We have 1 oxygen here. So we know we'll have to multiply this by 4 to end up with 4 oxygens. So that multiplier is going to go in front of my compound that contains oxygen. So now 4 times 1 is 4. But it's also going to end up multiplying my hydrogen by 4 as well. So I'm going to end up with 8 hydrogens on my product side. All right. So now I can balance what's left. I've got 3 irons on my reactant side, and I have 1 iron on my product side. So now I'm going to have to multiply my iron by 3 on my product side. And for my hydrogens, I have 8 on my product side, and I have 2 on my reactant side. So I'm going to have to multiply that 2 by 4 to get 8. So I'm going to take that 4 and put it out in front of the hydrogen. And now all of my atoms are balanced. That's my balanced equation. Okay. Let's look at a reaction with polyatomic ions in it next. Our reaction, it's not going to really change very much when we have a reaction that has polyatomic ions in it. But the one thing that we really want to mention in reactions that have polyatomic ions is that you don't necessarily have to separate out the individual elements of a polyatomic ion in order to balance your equation. If you have a polyatomic ion that is present on both sides of the reaction and it hasn't broken apart from one side to the other, then you can treat it as a unit. So if you have like, we're going to look at the phosphate ion in this reaction. Phosphate ion is PO4. You don't have to break it apart into like 1 phosphorus and 4 oxygens. You can just keep it together on both sides. But we'll take a look at what I'm talking about there in a second. So this is going to be our reaction. Let's write out the words because we're going to have to make the formulas from these. We're going to have aqueous strontium chloride. And aqueous lithium phosphate. And it's going to form solid strontium phosphate. And aqueous lithium chloride. Okay, so let's make our chemical formulas first so that we can write out that skeletal reaction. We know that strontium is always going to have a +2 charge. Chlorine is always going to have a -1 charge. So our formula for this is going to be SrCl2, and it's aqueous. Lithium is always going to have a +1 charge. The phosphate ion has a PO4 formula with a -3 charge. So the compound is going to be 3 lithiums and 1 phosphate. And it's going to be aqueous. For our strontium phosphate, Our strontium is +2. Our phosphate is -3. So we're going to need 3 strontiums to get +6, and then 2 phosphates to get -6. And that has to be reflected in our chemical formula. And that's going to be a solid. And then our lithium is going to be a +1. Chloride's going to be -1. Okay. So now our next step doesn't change. We're going to keep track of everything on each side. We've got strontium, chlorine, lithium, and I'm going to keep my phosphate together as a unit because I have phosphate on this side and I have phosphate on this side. Okay, so 1 strontium, 2 chlorines, 3 lithiums, and I've got 1 phosphate. Okay, so that 1 counts as 1 phosphorus and 4 oxygens. On my product side, I've got 3 strontiums, I've got 2 phosphates, 1 lithium, and 1 chlorine. Right? In a reaction like this one, where everything is part of a compound and nothing is by itself, there's no free elements here, it doesn't really matter where you start. Okay? I'm going to start at the top and just work my way down and try to keep everything balanced. So I'm going to start with my strontiums, and I see this mismatch. And so I know that on my reactant side, I'm going to have to multiply that strontium by 3. And so I'm going to have to put that 3 out in front of my compound that has strontium in it. But that also means I have to multiply my 2 chlorine by 3 as well. So I'm going to have 6 chlorines on my reactant side, not just 2. So now I can move to my chlorines and compare. I know I have 6 on my reactant side now. I only have 1 on my product side. So I'm going to multiply my compound that has chlorine by 6. So I can have 6 chlorines on my product side too. So I'll take that 6 and put it in front of my compound that contains my chlorine. And that 6 is also going to apply to my lithium. So I'm going to multiply my lithium by 6 as well. All right. The only thing that's left, oh, well, I got to go back here now, actually. And I look and I have 3 lithiums here. I have 6 lithiums here. So I'm going to have to multiply that 3 by a 2 to end up with 6 lithiums on both sides. So I'm going to have to put a 2 in front of my compound that has lithium and phosphate in it. Okay, so that 2 is going to multiply my lithium by 2 times 3 is 6. And that 2 is going to apply to my phosphate as well. So actually making that one fixed now has evened everything out. What you're going to notice when you're balancing the reactions, and you can write this down if you're still not sure, but notice that we never change subscripts. When we balance reactions. Okay, so we never change these things. These are our subscripts. Those are never the things that we've changed. The only thing that we change when we balance chemical reactions is the coefficient out in front of the compounds. Okay, so these are the things that we're able to change. All right. Okay, let's look at another example here. They give us, say, balance the following chemical equation, and they've written it out for us in an unbalanced way, which is nice because it means that we don't have to translate the words into formulas. Okay. They want us to balance it. So we're going to go through. We've got 3 sodiums. We've got 1 phosphate ion. We've got 1 magnesium. And we have 2 chlorines. And on our product side, I like to keep the elements and the polyatomic ions in the same order on both sides. So it's very easy for me to compare back and forth. So here I've got 1 sodium, I've got 2 phosphates, I've got 3 magnesiums, and I've got 1 chlorine. So I'm going to just start by balancing out my sodiums. So I'll put a 3 out in front. That means that I'm going to have to take that 3 and multiply it by my chlorines as well. All right. I'll move on to my next one. I've got 2 phosphates here. I have 1 phosphate here. So I'm going to put a 2. I'm going to multiply. I'm going to need to multiply my phosphate by 2, which means I'll have to put a 2 in front of my Na3PO4. Now, what happens here, and this is something that will happen when you balance reactions, is that sometimes you'll have to make changes to like coefficients that you're working with as you go, because you'll change something else and you'll be like, oh, well, look, that's changed the number of sodiums I have. So now I'm going to have to make a change here. That's fine because you just have to follow the process through. I'm putting a 2 in front of my Na3PO4. So that means I'm going to have to multiply the number of sodiums I have by 2 as well. So I don't just have 3 sodiums on my reactant side. I actually am going to end up with 6. Okay. All that means is that I have to go back to my sodium comparison here. And instead of multiplying my sodium from my sodium chloride by 3, I'm going to need to multiply it by 6. So instead of having just 3 sodiums and 3 chlorines, I'm going to have 6 sodiums. And I'm going to have 6 chlorines. Okay. But now my sodiums match and my phosphates match. So now I can go to my magnesiums. I'm going to need to multiply my magnesium compound on the reactant side by 3 so that I have 3 magnesiums on both sides. So I'll take that 3 and put it out in front of my magnesium compound. And I also have to take that 3 and use it to multiply my chlorines that are on my reactant side, which will give me 6 chlorines there. And now 6 and 6, 2 and 2, 3 and 3, 6 and 6. Perfectly balanced. Okay. You use that same procedure every time, then you're always going to be able to balance your reactions. All right, they give us a few reactions in the learning check to work on here. So we'll just go through one at a time. So our first reaction is Fe2O3. They put little blanks here for us. So in a reaction like this, where we have elements on their own, that's going to be the place that we're going to save those for last. That's going to be what we save for last. So we're just going to start out with our iron, our oxygen, and our carbon. And we're going to look at the oxygen in particular, and we're going to get that balanced out first. Okay, but we count up how much of each thing we have. And I'm going to focus on these oxygens, and I'm going to say, I want to get these two oxygens the same before I do anything else. So I'm going to take my oxygen on the left side. I'm going to multiply it by 2 to get 6. I'm going to take the oxygen on my right side and multiply it by 3 to get 6. Okay. But now I have to look at my other atoms. So the 2 also applies to the iron on my reactant side. So 2 times 2 means I have 4 irons. On my product side, I have to take that 3 and multiply it by my carbon as well, which means I have 3 carbons on my product side. But now I can fix what I'm missing here. I've got 4 irons here. I have 1 iron here. So I'll multiply this one by 4. I've got 3 carbons on my product side, 1 carbon on my reactant side. So I'll multiply that by 3. And that's my balanced reaction there. So my coefficients for that reaction, if you were like looking at this on the multiple choice, they might list the correct answer as 2, 3, 4, 3. And that would be our correct coefficients there. Our second example, Al plus FeO produces Fe plus Al2O3. Okay. And we're going to start off the same way. I've got aluminum, iron, and oxygen. One of each on my reactant side. I have got 1 iron, 2 aluminums, and 3 oxygens on my product side. Again, my aluminum and my iron are free elements, right? I've got my aluminum's free on my reactant side. My iron is free on my product side. So I'm going to balance my oxygen first because it's part of a compound on both sides. So I'm going to go to the oxygen on my reactant side. And I see that if I multiply it by 3, I'll end up with 3 on both sides. So I'll just take that multiplier of 3 and I'll put it right here. But that means that I have to multiply my iron by 3 as well. So now I can look at my product side and say, okay, well, I have 1 iron here. So I'll multiply that iron by 3. So now my irons will match. And now I can look at my aluminum. I've got 2 aluminums here and I have 1 aluminum here. So I'll multiply that aluminum by 2. And now my aluminums match. Okay, so 2, 2, 3, 3, 3, 3. And my list of coefficients for this one would be 2, 3, 3, 1. Because when there's no number out in front, then we assume that that number is a 1. Okay, we got 1 more to practice with. Okay, that's our reaction. So we have aluminum, we have hydrogen, and you see how we have the sulfate ion on both sides? We can keep that sulfate as a unit on both sides when we're counting. You can pull it apart if you want to. It seems like a little more work to me, but if you want to pull the sulfur and the oxygen apart and count them separately, you can do that as well. Um, here I'm going to balance, well, I'm going to count first, actually. I've got 1 aluminum, 2 hydrogens, and 1 sulfate. I've got 2 aluminums, 2 hydrogens, and 1 sulfate. So this one's easy. My only mismatch here is my aluminums. So I'm going to put a 2 out in front. And now everything else is already matched up. That's a really kind one to look at. So the coefficients the coefficients list that you would end up with for this would be 2, 1, 1, 1. Because you have 2 aluminums and you have 1 of everything else. And then all of your atoms are balanced. Okay. All right. So that's balancing. So let's take a look at the next part. We're going to look at the different types of chemical reactions, the different classifications of chemical reactions. You'll notice that there's some different things that happen in each type of chemical reaction. So we're going to look at the 5 main types of chemical reactions and just see the properties of them and see how we identify them. We have combination reactions, decomposition reactions, single replacement, double replacement, and then combustion. Okay, and each of these has their own like very particular pattern that you'll be able to identify. Starting with combination reactions, this is when you're combining things. Okay, so you're going to start out with 2 atoms or molecules, just 2 or more elements, and those are going to come together, join up, they're going to combine to form one product. So you start with multiple things on your reactant side, and you end with one thing on your product side. That's how you know it's a combination reaction. So these are just some examples of combination reactions for you to look at. Notice how there's always more than one thing on your reactant side and just one thing on your product side. All right. Sort of the opposite of a combination reaction would be your decomposition reaction, because your decomposition reaction means that you're starting with just one reactant and it's going to decompose or split into 2 or more products. Okay. So in decomposition reactions, you start with one thing and it splits up into 2 or more simpler things. All right. So if we look at our examples here, we start out with 2HGO, and it's going to split up into Hg and O separately. If we start out with 2KClO3, it's going to decompose or split up into KCl and oxygen separately. All right. So that's our decomposition. Combination reactions, combine things. Decomposition reactions, split things apart. Our next 2 reactions that kind of go together are our replacement reactions. We're going to have a single replacement reaction and a double replacement reaction. In single replacement reactions, you'll be able to tell it's a single replacement because you're going to start with an element in a compound on one side. And then on your product side, the element in the compound they're going to switch places. Something in your compound is going to switch places with your element. So notice that here we started out with iron by itself, and then the copper and the sulfate are together. Then on your product side, we have the copper by itself, and the iron and the sulfate are together. So one of the things switched places and took the spot in the compound, and then the other thing stayed by itself. In our second example, we have the zinc by itself, and the H and the Cl are together. And then on our product side, we have the zinc and the Cl together and the H by itself. Okay, so one element replaces another element in single replacement. That's where it gets its name, because only one element is going to replace another element. In double replacement reactions, we're going to have two elements replacing each other. Okay. So if we look at our examples here, we have ZN and sulfur, and we have H and Cl. And now on our product side, the ZN is going to move over here and attach to the Cl, and the H is going to move over here and attach to the S. So we get two things switching places in a double replacement. And that's why it's called double replacement, because we have two things switching. For AgNO3 and NaCl, what do we end up with? We end up with AgCl and NaNO3. So the Ag and the Na both switch spots. Okay. And the fifth type of reaction that we'd want to be able to visually identify is a combustion reaction. And combustion reactions are reactions that are going to produce heat. So we have it listed here as plus energy. That energy specifically is heat energy. Okay, so anytime that you're burning something, that is combustion reaction. And you're always going to see a release of heat as a product in these combustion reactions. All right. So that is our summary of the different reaction types. Okay, 5 of them. And you definitely should be able to just look at a reaction. And if it fits into one of these categories, you should be able to label it that way. Okay, you're definitely going to be expected to do that. So let's take a second here. Identify each reaction as one of the 5. So when we're looking at this first one, what are we going to look at? We're going to say, all right, I've got an element by itself, and then I've got a compound. And on my product side, I have a compound and I have an element by itself. That pattern is usually indicative of a single replacement. It means you have a free element and it's going to take the spot in this compound. And now this other thing is going to take the spot of the free element. So the one thing is going to replace another thing in this reaction. And that is going to be our single replacement. Okay, in our second example, we have sodium and sulfate and silver and nitrate. And on our product side, we have the silver with the sulfate and the sodium with the nitrate. So both the sodium and the silver switch places on our product side. And so that's going to be an example of a double replacement. All right, SR for single replacement. Our third example, we have nitrogen and oxygen combining to make NO. So that's going to be a combination reaction. And in our last reaction, we have a carbon compound combining with oxygen, and it's producing 3 things that always indicate combustion: carbon dioxide, H2O, and energy. That right there, that's how you know that that's going to be a combustion reaction. My really sad mouse handwriting. Okay, that's going to be combustion. Okay, erase. Okay. A few more. Again, I would recommend taking a second and just trying these out if you haven't. Our first one, we have barium and nitrogen separately, and then they combine to make barium nitride. They're combining to make something bigger, so that's a combination reaction. Our second example, we have a single element plus a compound. And on our product side, we have a compound and a single element. That means that one thing on our reactant side replaced one thing on our product side. The silver and the hydrogen switch places. So that is going to be an example of a single replacement reaction. For our next one, we have carbon plus oxygen, a hydrocarbon. It's like C2H6 means a carbon containing compound. Um, so a hydrocarbon plus oxygen produces carbon dioxide, H2O, and energy. That is going to be a combustion reaction. That energy as a product, that's a combustion reaction every time. Part D, we have the lead and the chlorine, the potassium and the sulfate. And we see on our product side, our potassium and our lead have switched places. Both of them have switched places. That is an example of a double replacement reaction. These two things have switched spots. And in our last example, we start out with one compound and we end up with two smaller compounds. So we took one thing that was larger and it converted into two things that are smaller. It's split apart. That is an example of a decomposition reaction. Erase. Hopefully that makes sense. Let's look at another type of reaction called oxidation reduction reactions. We want to figure out what these terms mean. We want to be able to figure out what's being oxidized and reduced in the different reactions that we're looking at. Okay. Oxidation reduction reactions are a very good source of energy, and this is because oxidation reduction reactions require the transfer of electrons to occur. We see them very often in processes like this one when we have iron and oxygen combining to form rust. That's an example of an oxidation reduction reaction. A lot of the reactions that provide energy in the form of batteries, oxidation reduction reactions. In any oxidation reduction reaction, electrons are going to be transferred from one substance to another. So one of our reactants is going to lose electrons and give them to the other reactant. That reactant is going to gain the electrons. The reactant that lost the electrons is the reactant that was oxidized. The reactant that gained electrons is the reactant that is reduced. Okay. These are just two terms, like two of those like mnemonic devices that you can use to help you memorize which is which. Leo and Ger. Losing electrons is oxidation. Gaining electrons is reduction. Or oil rig. Oxidation is loss of electrons. Reduction is gain of electrons. Either of these things works fine, but it does help to, help you remember what's happening, which is which. Again, we see oxidation reduction just in many places that you won't realize that it's oxidation and reduction if you don't know what oxidation and reduction means. The shorthand term for oxidation reduction is redox. So when we call something a redox reaction, we're saying that oxidation and reduction are happening within that reaction. Oxidation and reduction are a coupled process. That means that you can't have oxidation happen by itself and you cannot have reduction happen by itself. If oxidation is happening, reduction is happening as well, and vice versa. So that's why you get the combined name of redox, because both of these things have to be happening at the same time if either is going to occur. So one way you can identify redox reactions and classify them as oxidation or reduction is you can look if electrons are listed within the reaction itself. You can look to see whether the electrons are on your reactant side or your product side. Okay, and what we're going to see is that if electrons are listed as products, that indicates that oxidation has happened, because oxidation means a loss of electrons. Okay. And if electrons are listed as reactants, that indicates reduction, because reduction means that you're gaining electrons. All right. So in the examples that they've given us in the learning check for the first one, they're not giving us full reactions here. They're just giving us like half reactions. And they're saying identify the process as oxidation or reduction. So for our first one, when we start out with tin and we end up with a tin ion and 4 electrons, that means that tin has just lost its 4 electrons, right? So our electrons are on the product side. The tin lost its 4 electrons and got more positive. This is oxidation. In the second example, we have an iron ion, and it's gaining 1 electron, and it's going to become a less positive iron ion. So its charge went from +3 to +2. So it gained an electron. That's reduction. And we have Cl2 plus 2 electrons produces 2 chloride ions. So our chlorine gained 2 electrons and it formed 2 negatively charged chloride ions. It gained electrons. That's going to be reduction. All right. In the next learning check, they give us a more complete example, and they try to ask us to figure out what's been oxidized and what's been reduced in this example. And we're going to ask ourselves the same question. So the full question says, in light-sensitive sunglasses, UV light initiates an oxidation reduction reaction, which they're writing as this. Okay. And now where the questions here are, what is oxidized and what is reduced? The only things that can be oxidized or reduced are your reactants. Your products are the result of the oxidation and reduction. So when we're looking to see what is oxidized, it's going to be one of these 2 reactants. When we're looking to see what is reduced, it's one of these 2 reactants. All right. But we have to ask ourselves, if we have an Ag with a plus and it turned into an Ag that's got no charge, did it gain an electron or did it lose an electron? If it loses an electron, that means it's going to get more positive. If it gains an electron, that means it's going to get more negative. So if our silver went from being +1 to being neutral, it got more negative, which means it must have gained an electron, which means it must have been reduced. So our Ag plus had to be reduced. And if our Ag plus is reduced, then our Cl minus had to be oxidized. But we can also prove that asking the same questions. You don't just want to, like, I would say at this point when you're still learning this, don't just figure out one and then be like, all right, I know the other. We know that the chloride is probably correct here, but now we're going to prove it to ourselves. If chloride is the thing that's oxidized, then we know that it should get more positive on the product side. And what happened here, it went from -1 and its charge went up to 0, right? So it must have gotten more positive for its charge to be 0. So if it got more positive, that means that it was oxidized. So our Cl- is going to be oxidized. Our Ag+ is going to be reduced in this reaction. When you're looking at oxidation reduction reactions, there are some ways that you can tell whether oxidation or reduction is happening. Share my screen again so you can see the words here. There's things that you can look for. If a reaction lists the charges or lists electrons, you can look at the change in the charge or the change in the electrons to figure out what has been oxidized and what's been reduced. We saw that in the last few examples. Other ways that you can figure out that oxidation is occurring, you can see that oxygen has been added to something or hydrogen has been removed. Those are two things, that indicate oxidation is occurring. Reduction is going to have the opposite, like the opposite triggers, descriptors, the opposite processes. So for reduction, instead of a gain of oxygen, you're going to have the loss of oxygen. For reduction, instead of losing hydrogen, you'd be gaining hydrogen. So if you don't have charges explicitly written in your reaction, you can also use these two things to tell you whether oxidation or reduction has likely occurred. We can also use what are called oxidation numbers to help us figure out where the electrons have gone in a reaction. Oxidation numbers look exactly like charges, but they're imaginary values. Okay, we're going to kind of just use them as bookkeeping to understand where our electrons have gone through or where they have gone to. And there are 5 rules that we can use to assign oxidation numbers to elements in a reaction. And if we assign oxidation numbers, if we take the time to use these rules to assign oxidation numbers, then we'll never have to guess whether oxidation or reduction has happened or where it's happened, because we'll be able to see the change in number, and that change in number will tell us what is being oxidized and what is being reduced. So these are the 5 main rules, okay? And I would say that for now, just keep them next to you while you're doing oxidation reduction problems, so you can get used to them. You have to follow these rules in order. If any of these rules conflict with each other, you follow the one that came first. Okay, so like if rule 1 conflicted with rule 4 for some reason, you'd follow rule 1 first. Within rule 5, you'll see a whole bunch of elements just listed, right? Like the oxidation state of fluorine is usually -1. Hydrogen is usually +1. Notice how they kind of mimic their charges. But if the rule for hydrogen ever conflicted with the rule for oxygen, you'd have to follow hydrogen's rule first because hydrogen comes first on the list. Okay. You'll notice though that most of the elements that are part of compounds, they're going to have oxidation states, or the term oxidation state and oxidation number, you can use those interchangeably. Elements are generally going to have oxidation states that are the same as their actual charge whenever they can. The only time that they don't have oxidation states that match their charge, their typical charge, is when there's a conflict. Okay. The first rule, the most important rule that we're going to have to recognize, is that any element that's by itself, that's not part of a compound, and that's neutral, is going to have an oxidation state of 0. and any ion that's by itself. Like if you have Na plus all by itself or Cl minus all by itself, the oxidation state of that ion is going to be equal to whatever the charge on that ion is. All right. Those two are pretty important when you're looking at oxidation states. After rule 3, the rest of these all deal with oxidation numbers for elements that are part of compounds. All right. When you look at the oxidation states of different elements in a neutral compound, all of the oxidation numbers should add up to 0, just like the charges should add up to 0. If you're looking at a polyatomic ion, all of the oxidation states in a polyatomic ion should add up to the charge on that ion. Again, just like we were dealing with charges. So you see, like, there's a lot of overlap between oxidation numbers and charges. But let's just talk through some of these examples so that you can see what we're talking about with these assigning oxidation numbers. Okay. And I would say for each of these, like, write down one of these reactions, flip back to the slide with the list of rules on it, and try to assign the oxidation numbers on your own and see how it goes. 2 plus. Okay. For this one, I have an entire reaction that is filled with monoatomic ions. Okay, ions that are only one atom. Okay, remember, polyatomic ions are things that are like this, when we have a whole bunch of atoms connected together and they have a charge overall. A monoatomic ion means that we just have iron, and that iron has a +2 charge. Like, yeah, we have 2 of these things, but we're looking at an iron by itself that has a +2 charge. There just happens to be 2 of them. Okay. So for each monoatomic ion, you can use rule 2 and you can say, all right, well, each of the irons here is going to have a +3 oxidation. The tin here is going to have a +2 oxidation. Each of the irons here is going to have a +2 oxidation. And the tin here is going to have a +4 oxidation. So the oxidation numbers just literally match the charges. When you're working with oxidation and reduction numbers, you do not have to worry about the coefficients in the front, because you're just tracing the oxidation number changes from one side to the other. So you could count each of these, but you would just see that instead of looking at the iron and saying, well, the iron's going from +3 to +2, you would just be doing the same thing twice. Okay, so we don't have to look at the coefficients when we're doing oxidation reduction, because we should already have our balanced reactions. Like, that's how they're given to us. Watch what happens when we look at the oxidation numbers and we track the changes here, though. You're going to track from element, the same element, you're going to connect on both sides of the reaction. So here, my iron went from +3 and it went down to a +2. Okay, so my oxidation number decreased. When your oxidation number decreases, that means that whatever you started with, your reactant, it got more negative. If it gets more negative, that means it's gaining electrons. So if your oxidation number decreases, that means that that substance is undergoing reduction. So we can tell from that decrease in value from reactant to product that the iron is reduced. And then if we look at our tin, it goes from +2 up to +4. When our oxidation number increases, that means that our substance got more positive, which means that it lost electrons. Okay. So when our oxidation number increases, that tells us that oxidation happened. So in this example, our tin is oxidized. Okay. So our Fe3 plus is reduced and our SN2 plus is oxidized. It gets more positive on the product side. Our Fe3 plus is reduced. It gets more negative on the product side. Let's look at an example where this is more helpful for us when we're looking at reactions that don't have charges in them. This reaction was kind of easy to look at because it had charges, and we could literally look at the charges and we can say, this went from +3 to +2. That means it got more negative. So that means that it had to be reduced. Tin went from +2 to +4, it got more positive. So that means tin had to be oxidized. You don't have to assign the oxidation numbers in this example to figure out whether something was oxidized or reduced, because we could look at the charges. But there are reactions where we don't have charges to look at. And that's when using our oxidation numbers is going to be even more helpful. So in our second example, we have Cl2 plus 2 NaBr produces 2 NaCl plus Br2. Okay. Now in this one, there are no charges to look at. So now we have to figure out the oxidation number of each of the components so that we can track the change that happened. Where did the electrons go? It's not obvious right away. So the first thing that we're going to do is we're going to look at this reaction and we're going to identify our free elements. Okay. Our chlorine here is a free element, meaning it's not part of a compound. And our bromine is a free element, meaning it's not part of a compound. And whenever we have a free element, rule number 1 says that our oxidation number for these is going to be 0. Okay, so we figured those out. Now we have NaBr and NaCl. Our fourth rule, rule number 4, tells us that any metal that's part of group number 1, okay, so this is rule 4, any metal that's part of group number 1 that's in a compound is going to have an oxidation of +1. So sodium's oxidation is going to be +1 in both of these compounds. Okay. And what rule number 3 tells us is that when we add the oxidation of sodium and bromine together, that they have to add up to 0, just like with charge balance. So if sodium has a +1 oxidation, then bromine in the NaBr has to have a -1 oxidation. And on our product side, the same thing. Rule 3 tells us that our sodium and our chlorine are going to have to add up to 0. So if sodium's oxidation is +1, then chlorine's oxidation has to be -1. Okay. And again, you can include the coefficients in this. You just have 2 plus ones and 2 minus ones. So you don't have to include it. You don't have to include the coefficients for this if you do not want to. But now let's look at the change that happens here. Okay. When we compare our reactant side to our product side, start out with our sodiums because our sodiums don't change. There's no change in number here. So what we know from that is that sodium is not oxidized or reduced. Whatever doesn't change is not oxidized or reduced. Our chlorine goes from an oxidation of 0 and it goes down to an oxidation of -1 on our product side. It went from 0 to -1. So it got more negative. And if it gets more negative, that means that it gained electrons. So our Cl2 is reduced. It gained electrons and it got more negative. Our bromine, on the other hand, it went from a -1 and it went up to a 0, right? 0 is more positive than -1. So that means that our bromine must have lost electrons to get more positive. So our bromine is oxidized. Okay. Let's try one more example. All right. So for this one, we're going to want to start the same way. The one thing that we have to look at in this case that we haven't looked at yet is we have compounds with polyatomic ions that are part of them. When you have a compound that has a polyatomic ion in it, you're going to have to find the oxidation numbers of your polyatomic ions first, and then find the oxidation of the metal that it's attached to second. Okay. Which is a little bit of a different order of operations there. Let's start out with our free elements. We know that our iron here is going to be 0 because it's a free element. Our copper here is going to be a 0 because it's a free element. In this compound, when you have polyatomic ions, right, we know that this is a sulfate ion. So we know that in your sulfate ion, remember what our rule number 3 said. It says that the oxidation number of your polyatomic ions are going to add up to the charge of your polyatomic ion. Okay? So that means that when you add all of the oxidation numbers of the sulfur plus the 4 oxygens together, those are all going to add up to -2. If your sulfur and your oxygens all add up to -2, that means that the oxidation number on your copper has to be a +2. Because when I add my copper and my sulfate together, it has to add up to 0. Because my compound is neutral overall. So the oxidation of the sulfate ion by itself is -2. The oxidation number of the copper is +2. And when I add them together, it equals 0. Okay. Same thing is true over here. I've got my iron and my sulfate. The oxidation number of my sulfate as a polyatomic ion is -2. That means that the oxidation number of my iron here has to be positive too. All right. That's why, when you can use some of the knowledge that you've already had from charge balancing to help you with these oxidation numbers. Once you look at the oxidation numbers, now you're going to be able to track the change that happens. Iron goes from 0 to +2. Iron gets more positive, so it must have lost electrons. So your iron is oxidized. Your copper went from a +2 down to a 0, so it got more negative. That means it must have gained electrons. So your copper is reduced. And because your sulfate ion, it doesn't change in oxidation number, that means that your sulfur and all of your oxygens were not oxidized or reduced. Okay. So that is how you can work with oxidation and reduction. All right, so the next thing that we're going to talk about is called the mole. This is all going to kind of build together for us to do some calculations with chemical reactions later on. The mole is a term that's used in chemistry. They call it a counting term. It's like the same way that you'd use the term a dozen, right? When you use the word a dozen to describe something, it means that you have 12 of that thing. When we use the word mole, it means that very specifically we have 6.02 times 10 to the 23 of that particular thing. The reason why we have a specific term for when we're talking about, the chemistry terms is because we have atoms, molecules, ions that we're working with, and all of these things are really, really tiny. And so we need a number to represent things that are super small. Okay. So when we have 1 mole of something, that means we have 6.02 times 10 to the 23 of that thing. And this value is called Avogadro's number. Okay. The name, like a lot of things that you see in your sciences, named after a scientist from a long time ago. All right, so this is a number you should know. All right, so you can write it as an equality. Every 1 mole of something equals 6.02 times 10 to the +23 of that thing. So if you're talking about a mole of an element, that means you have 6.02 times 10 to the 23 atoms of that element. So a mole of carbon, you have that much atoms of carbon. 1 mole of sodium means you have that many atoms of sodium. The equality works for anything that you're talking about. Okay, so again, here's a mole of aluminum and sulfur. Both of these are elements. And so for each of these, 1 mole describes 6.02 times 10 to the 23 atoms of those elements. When you're talking about molecular compounds, like say we have a mole of water or a mole of vitamin C, we're going to have 6.02 times 10 to the 23 molecules of those compounds. Okay. 1 mole of sodium chloride means we have 6.02 times 10 to the 23 formula units of sodium chloride. So 1 mole just means Avogadro's number, which is 6.02 times 10 to the +23. Because we can write Avogadro's number as an equality, that means that we can turn Avogadro's number into a conversion factor when we're asked questions about quantities that include moles or atoms or particles or molecule numbers. Okay, and we can set up our conversion factor depending on the question that we're asked. So for example, let's look at this first number. This first question. Avogadro's number is used to convert moles of a substance to particles. How many CO2 molecules are in 0.5 moles of CO2? Okay, so let's look at how we would solve out that problem. So the question is, how many molecules are in 0.5 moles of CO2? We can start by writing out our equality between moles and Avogadro's number. If we have 1 mole of CO2, and CO2 is a molecule, that means that we're going to have 6.02 times 10 to the 23 molecules of CO2. Okay, so 1 mole means that we're going to have 6.02 times 10 to the 23 molecules of that substance. So if we have 0.5 moles of CO2, then we're going to set up our conversion factor based on our quality. And when we set up our conversion factor, we're going to take the unit that matches the unit that we start with, and we're going to put it on the bottom so that it cancels out. And then we're going to put our other value from our quality up top. Okay, so we're going to do 6.02 times 10 to the 23rd times 0.5, 3.01 times 10 to the 23rd molecules of CO2 are in 0.500 moles. Okay, so we made our equality between 1 mole and Avogadro's number. We took the number that I started with, that we were given, and then we used our equality to set up our conversion factor. The unit that we're given in the problem is the unit that goes in the bottom, and then our other unit goes in the numerator spot. All right. The next question in our slides is the learning check that says the number of atoms in 2 moles of aluminum. And then they give us some multiple choice answers that we can look at as well. And I would suggest, again, trying all of these out on your own first. Okay, so the first thing that we can do is we can write out our equality. 1 mole of aluminum, aluminum is an element. 1 mole of aluminum is going to be 6.02 times 10 to the 23 atoms of that element. You're going to notice that for Avogadro's number, we can write this out for ourselves. If we have a molecule, then Avogadro's number is going to tell us the number of molecules that are present. If we have an element, then Avogadro's number is going to tell us how many atoms are present. Okay. But keep that in mind when you're making your equality. That's why in our last example with CO2, 1 mole of CO2 gave us 6.02 times 10 to the 23 molecules of CO2. That's because CO2 it's not an element, it's a compound. Let's write that word up here too, in case that's an easier. So we'll say if it's a compound or a molecule that you're given information about, Avogadro's number is going to be related in terms of molecules. But if it's an element that you're given information about, Avogadro's number is going to relate to the number of atoms of that element. Okay. So now in our example, we have 2 moles of aluminum specifically. And so when we set up our conversion factor, we're going to put the unit with moles in it on the bottom. And then Avogadro's number up top. And we're going to end up with 1.2 times 10 to the 24 aluminum atoms in that sample. Okay. The next question has us it's asking something a little bit different. This time they're going to give us a number of atoms and they're asking us to figure out the number of moles. Number of moles of sulfur in 1.8 times 10 to the 24 atoms of sulfur is, and then they have us solve it out. We can start the same way by writing out our equality. If we have 1 mole of sulfur, and sulfur is an element, that means that we're going to have 6.02 times 10 to the 23 atoms of that element. Okay. But this time, the information that they've given us is this. So when we start out, we have 1.8 times 10 to the 24 atoms of sulfur. So now when we set up our conversion factor, the part of our equality that has atoms of sulfur in it has to be the thing that goes in the bottom. Okay. So we're going to take this term and we're going to put that on the bottom. And then we're going to put our 1 mole up top. And when you're solving this out, remember that things that are on the denominator part of your conversion factor, these are going to get divided. So when you're putting this in your calculator, it's going to be 1.8 times 10 to the 24 divided by 6.02 times 10 to the 23. Okay. The other thing that I would recommend is making sure that when you're putting this into your calculator, you use parentheses around this value. Okay. Because if you're not using the scientific notation keys specifically on your calculator, and a lot of people don't use the scientific notation keys when they're inputting these numbers, a lot of people will put this in as 6.02 multiply 10 and then exponent 23, something like that. When you do it like that, the calculator will read your order of operations incorrectly. And so it won't divide the whole term. It will only divide the first part of the term, and then it will multiply the rest by 10 raised to the 23. And the problem with that is your answer that you get will have the correct first digit, like the first term of your scientific notation will be correct, but your exponent will be wrong. Okay. Um, so to make sure that doesn't happen, you can put any term that's in the denominator that you know you're going to be dividing in your calculator. You can put it in parentheses, and then that will eliminate the problem. Okay. So when you put this calculation in, first of all, notice that your atoms of sulfur are going to cancel out. So you're going to be just left with moles of sulfur at the end. We're going to be left with 2.9900, which we're going to be rounding to two significant figures. So this will be 3.0 moles of sulfur. That will be our final answer. Okay. But when you put this in, if you end up getting 1.1 times 10 to the 48, that means that you need to go back and you need to put the parentheses around those. Okay. Um, let's look at how our chemical formulas are linked to our mole values. How we can look at our chemical formulas and we can relate those to the mole values as well. When you have a chemical formula, like they give us the formula for aspirin here. Oh, let me get my, there we go. You're seeing that one molecule of aspirin, which is C9H804, or 1 mole of aspirin, is going to have 9 carbon atoms, 8 hydrogen atoms, and 4 oxygen atoms. So if we have 1 molecule of aspirin, these are our number of atoms for each of those things. Okay. If I have 1 mole of this element, that means that I'm going to have to um, multiply the mole value, my 1 mole of my element. I'm going to have to multiply that by the number of each atom that I have present, meaning that if I have 1 mole of aspirin, within that 1 mole of aspirin, there's going to be 9 moles of carbon, because for every 1 molecule of aspirin, there's 9 atoms of carbon. For every 1 mole of aspirin, there's going to be 8 moles of hydrogen and 4 moles of oxygen, because for every 1 molecule of aspirin, there's 8 hydrogen atoms and 4 oxygen atoms. Okay. We're going to be able to take this and we are going to be able to write equalities from these. Okay. So we're going to practice that next. What we're going to see as we make these equalities is that the equalities are going to come from the actual chemical formulas. So this is like a better breakdown. We're going to be able to use this. 1 molecule, 9 atoms, 1 mole, 9 moles of the specific element. 1 molecule, 8 atoms of hydrogen, 1 mole, 8 moles of hydrogen. Okay. So the atom and the mole ratio are going to correlate with each other, just like the molecule and the mole amount. All right. So we're going to be able to set up conversion factors from those equalities. And when we set up these conversion factors, remember for each equality, we're going to be able to write 2 conversion factors from that. So for each atom in an aspirin molecule, we're going to be able to write 2 conversion factors for each of those atoms, each of those elements. Okay. And then we're going to be able to use those to answer questions about the specific numbers of atoms of an element that are in a sample. Okay. Um, we'll look at this question to start with. This one says, how many atoms of oxygen are in 0.15 moles of aspirin? And they give us the chemical formula. Okay, so we're going to need two different relationships here to answer that question. Okay, we have they're asking us how many atoms are in 0.150 moles of aspirin, which is C9H804. Okay, so what we have to remember is that with Avogadro's number, if we have a compound, Avogadro's number can tell us the relationship between 1 mole of that compound and the number of molecules of that compound we have present. Okay, so for every 1 mole of aspirin, we're going to have 6.02 times 10 to the 23 molecules of aspirin. That's what Avogadro's number can tell us. What our chemical formula can tell us is how many moles of oxygen are in every mole of our aspirin compound. Okay. Or our aspirin molecule. So if we have 1 molecule of aspirin, we know that every one of these molecules of aspirin is going to have 4 oxygen atoms. Okay. Um, we also know that based on what we just looked at in our last slide, every 1 mole of CnH804 tells us that we have that many moles of oxygen atoms. All right. So there's 2 ways to approach a problem like this. If we're told the moles of our aspirin, we can there's 2 pathways to take. And I don't want to limit the way that you're thinking about this question, but I don't want to tell you that there's only one correct way to solve this, but you have to understand the connections that you're making. Okay. So I'm going to draw a little split right here because those top 2 involve one way that you can solve this. And these bottom 2 things that I'm going to write involve the second way that we can solve this. Okay, and they're both based on the same equivalencies, Avogadro's number, and then the relationship between our aspirin compound and the number of oxygen atoms that are in it. Okay, so when you're looking at this question and you're starting out with 0.150 moles of aspirin, the first thing that you can do is you can figure out using Avogadro's number how many molecules of aspirin are in 0.150 moles. That would be a valid first step. All right. So I'm going to draw a line under here and we're going to solve this out. This is going to be solution A. This is going to be solution B. So for solution A, the first thing that I'm going to do is start out with my 0.150 moles of my aspirin. And I'm going to use Avogadro's number, which tells me that every 1 mole is going to give me 6.02 times 10 to the 23 molecules of aspirin. Okay. So that's my first conversion factor that I use there. The second step, solving it this way, I have to go from molecules into oxygen atoms. So I'm going to have to look at my chemical formula and I'm going to have to say, all right, well, for every 1 molecule of C9H8O4, there are 4 oxygen atoms. All right, and notice how everything cancels out. This is your mole value canceling out. The molecule unit here, I should have written out 1 molecule here. Pretend that I wrote the molecule word there. Every 1 molecule of C9H8O4 has 4 oxygen atoms. I think I said it, but I didn't write it. So now when I do my math across, I'm going to be left with the number of oxygen atoms that are present in my sample. So I'm going to do 0.15 times 6.02 times 10 to the 23 times 4, which gives me 3.61 times 10 to the 23 oxygen atoms. It's a perfectly good way to solve that problem. The second way that you can solve this problem uses the relationships that we listed out here. We can start out with our moles of aspirin, and we can figure out how many moles of oxygen atoms are present. And once we know how many moles of oxygen atoms are present, we can use Avogadro's number and relate moles of oxygen to atoms of oxygen. Okay. We're going to end up with the same set of relationships. We're just taking a slightly different path to get to the endpoint. So we can start out with our 0.150 moles. And then we can use our relationship saying that every 1 mole of aspirin is 4 moles of oxygen. Okay, so our moles will cancel out. And then we can use Avogadro's number that tells us every 1 mole of oxygen is 6.02 times 10 to the 23 oxygen atoms. Okay, and we're still going to end up with 3.61 times 10 to the 23 oxygen atoms. Okay. Either of those pathways works fine. What's important is that you don't force something, and that you write down the units that you're working with. Because if you remember to write down your units as you go, then you won't miss a step. Okay. It'd be really easy in a case like this to miss one of the conversions here because you didn't write down what the number represented. So here we're writing down that like 0.150 represents moles of this compound. And then in your next step with your conversion factor, you're going to put moles of that compound on the bottom so that the units cancel out and the number of molecules up top. But by writing out what each number means, it means you're going to be more likely to put it in the correct position because you know that the units need to cancel out as you go. All right. Okay. The next thing we're going to look at is calculating the molar mass. Let me share my screen again. We've looked at molar mass. Well, you've been looking at molar masses really all semester, every time that you've looked at your periodic table. When you looked at the atomic mass values that are on your periodic table, we've represented these in terms of AMU, or atomic mass units, before. Okay. Another way that we can use these numbers on the periodic table is we can say that these values represent the grams of that particular element in 1 mole of that element's atoms. Okay. What that is going to give us is an alternate set of units that we can use that relate the mass of an element to the number of moles of that element. Okay, so we're going to use our periodic table, and we are going to now apply the masses of individual elements to the compounds that these elements form. Okay, so let's take the example that they're giving us here, rather, is lithium and carbon. Okay, so each of these is an individual element. If we wanted to look at the periodic table and we wanted to find the mass of each one, carbon has an atomic mass of 12.01 AMU. Lithium has an atomic mass of 6.941 AMU. But we can represent this as a molar mass instead, and we can say that every 1 mole of carbon is going to equal 12.01 grams of carbon. Okay. The units for molar mass are always grams per mole. 12.01 grams in 1 mole. 6.941 grams of lithium in 1 mole of lithium. All right. But we can write out those values as equalities, which then is going to let us form conversion factors with them. Okay. You can see they're pulling out all of the different elements here: silver, carbon, sulfur. Each of these values we've already looked at in terms of atomic mass units, but now we can look at them in terms of molar masses and say that there is 107.9 grams of silver in every 1 mole of silver, which means that there's 107.9 grams of silver in 6.02 times 10 to the 23 atoms of silver. Okay. We can calculate the molar mass of larger compounds as well using our periodic table values. So when you're given a compound like the one here, they give us the compound lithium carbonate. If we want to find the molar mass for this compound, we're going to figure out the number of atoms of each element that are in this compound. And then we're going to use our periodic table, and we'll say, all right, there's 2 lithiums in this compound. So I'm going to multiply the mass of lithium by 2. There's 1 carbon, so I only need 1 carbon mass. There's 3 oxygens, so I'm going to multiply the mass of oxygen by 3. And then I'm going to add all of those mass values together to figure out the overall mass of the lithium carbonate. Okay. That would be our approach to solving this. So this will start out with us writing the formula. And at the very beginning of this, when you're first learning how to do this, it would make a lot of sense if you, I like to break things down dramatically. So I would list the elements underneath the compound, and I like to write down how many of each element there are. So I have 2 lithiums, I have 1 carbon, and I have 3 oxygens. Now I'm going to go to my periodic table. I'm going to find the molar mass for each element. So for lithium, it's 6.941. For carbon, it's 12.01. And for oxygen, it's 16.00. And then we'll add those all together. And we're going to get 73.892, which will round to 2 decimal places. So it'll be 73.89. And the unit for molar mass is grams per mole. Okay. And if this is our unit, grams per mole, what that means is that we can turn that into that equality that we saw in the last slide. There's going to be 73.89 grams of the lithium carbonate in every 1 mole of the lithium carbonate. Okay, that's what our molar mass, that's the information our molar mass is going to give us. So let's look at 2 examples. In the next learning check, we're going to look at the molar mass calculations for 2 different compounds. And then we'll write out the equalities for each one. Example 1 is C2H6O. And example 2 is NH4 3PO4. Okay, so we're going to find the molar masses of both of these things. So for starters, with our C2H6O, where our compound is made of carbon, hydrogen, and oxygen. 2 carbons, 6 hydrogens, 1 oxygen. Then we go on our periodic table. The molar mass for carbon is 12.01. The mass for hydrogen is 1.008. Oxygen is 16. Okay, and then we'll add all these together. And we're going to end up with a final mass of 46.07 grams per mole when we round it. And then we can turn that into our equality. So every 1 mole of our C2H6O is going to be 46.07 grams. Okay. And for example 2, we have our ammonium phosphate. This one's more interesting because we've got parentheses and subscripts and things like that. But we're going to start the same way. We're just going to list out the elements that are present. We have nitrogen, hydrogen, we have phosphorus, we have oxygen. So for our nitrogens, because the 3 is outside the parentheses, we know that it's going to apply to both things in the parentheses. So we're going to have 3 nitrogens. For our hydrogen, we're going to have 4 times 3 total, which is going to be 12. I'll put a little multiply after that. We have 1 phosphorus and we have 4 oxygens. And now we're going to multiply these numbers by the molar masses from the periodic table. Times 3. Okay, and then we'll add those all together. and we get 149.10 grams per mole, which means that there's going to be 149.10 grams of ammonium phosphate in every 1 mole of ammonium phosphate. Okay. So that's how we calculate our molar mass. And now we want to use this as part of our calculations. Okay. So what we're going to see, let me share the slides again just so we can look at the steps real quick. We're going to be able to take our molar mass values of our compounds, and we are going to turn those equalities that we've been writing down into conversion factors so that we can use actual masses of these compounds and then figure out how many moles are present. And then we can figure out how many molecules are present and maybe even atoms if we want to go that far. But we're going to be able to do a lot more with the values that we're given if we're able to relate the masses to the mole values as well. Okay. So we'll take the molar masses that we calculate and then we'll represent them as conversion factors, which are these ratios or fractions that we've been using all semester. And it's going to allow us to relate grams and moles. All right. So we'll look at some examples of this because this is another thing, I think, kind of like with everything we've talked about so far in this chapter. The theory is fine, but seeing the examples is where the words start to really make more sense. So our first example, we have a box of table salt, NaCl, contains 737 grams of NaCl. And they ask us how many moles of NaCl are in that box. Okay, so how many moles of NaCl are in 737 grams of NaCl? Right? That's what the question really comes down to. Right? So the first thing that we want to do, whenever we're connecting moles of something to grams of something, whenever we're making this connection, whether it's moles to grams or grams to moles, we always make this connection using the molar mass. That's the only way to do it. So because they want us to go into moles from our grams, we know we're going to have to find the molar mass of our NaCl first. So the molar mass of our NaCl, we're going to take the mass of 1 sodium and the mass of 1 chlorine, and then we'll add them together because we only have 1 atom of each in this compound. We add those together. And we're going to end up with a molar mass of 58.44 grams per mole, which we can write out as our equality. There's going to be 58.44 grams of NaCl in every 1 mole of NaCl. All right. So if I'm starting out with 737 grams of NaCl, I can look back at my equality and I know that I'm going to want my grams of NaCl on the bottom. So I'm going to put my 58.44 grams on the bottom. And I'm going to put my 1 mole up top. And I'm going to end up with 12.6 0.6 moles of NaCl. Okay. Next example. A sample of FeSO4 has a mass of 59.8 grams. So we have 59.8 grams of FeSO4. How many moles of FeSO4 are in the sample? All right. So now we're working with FeSO4. So the first thing I want to do is find my molar mass for the compound. So I have 1 iron, 1 sulfur, and 4 oxygens. Okay, so I'm going to add that together. That's my molar mass. So I'm going to make my equality for that. Every 1 mole of FeSO4 is going to be 151.92 grams. So if I'm starting out with 59.8 grams, then when I set up my conversion factor, I'm going to want to make sure that my grams of FeSO4 goes in the bottom so that my units cancel out. And my mole value goes up top. Okay. Let's take a look at this kind of map that they've given us here. Um, this is a way that you can help visualize what you need to use to go from one calculation to another, as long as you can kind of map out the steps that you're taking. So like, for example, if you're given a mass and you need to go to moles, uh, every time you're going between grams and moles, you're going to need to use the molar mass. If you're going between mass and the number of atoms of something, you can go from, you can see from this map that you're going to start with grams. First, you have to go to moles. Then you can go from moles into atoms. Okay. Let's say that you're starting out with a compound and you want to know, you're starting out with a mass of a compound and you want to figure out how many atoms of a particular element in that compound you have. This is giving you a map to help you figure out how to do that. You start out with your grams of a compound. You can use the molar mass to figure out the moles of that compound. You can go from moles of the compound into the number of molecules using Avogadro's number, right? Moles and molecules. That's the connection when we have compounds. And then if we want to go into a particular number of atoms, we can, let's say, use our formula subscript and we can say, all right, well, in one molecule, I have X number of atoms. And then we can figure out how many atoms are present. Okay. But this map is going to give us a good way. It's a good tool to use while you're learning how to do this in case you get a little bit lost in the the action that you have to do in a particular step. What number do I have to use? What calculation do I have to make? Um, let's try one more problem. I'm going to make it up right now, so it's not in the notes, but it'll be a problem where we're given a particular mass value of a compound, and we'll figure out how many atoms of an element are in that compound. Okay, so let's say that I have I'll say how many oxygen atoms are present in 32.45 grams of CH3OH. No, something more interesting than that. We'll do glucose, C6H12O6. Yeah, that's better. How many oxygen atoms are present in 32.45 grams of glucose, C6H12O6? Okay, so now when you're looking at this question, like that's a lot of different things that you have to connect here. Okay, so you can start by looking at the values that were given, the 32.45 grams. And you can say to yourself, anytime that I'm given a gram value, I can always convert that into moles. And anytime that I make this connection, I'm going to use the molar mass. Whenever you go between grams and moles, it's always the molar mass. So once you take this gram value, you can convert it into moles. What's the next thing you can connect your moles to? I have a compound here. So if I want to take my moles and I want to use Avogadro's number, I can relate the number of moles of my compound into the molecules of that compound. And I can go between moles and molecules using Avogadro's number. Once I know how many molecules I have, then I can figure out how many number of oxygen atoms I have specifically by using the subscripts in my chemical formula. Okay, so before we write out all of our steps to solve this problem, I want to write out each of the equalities that are being represented here. So the first thing I need to do is calculate the molar mass of my glucose. So I'm going to calculate the molar mass right here. Okay, so we have 6 carbons, 12 hydrogens, and we have 6 oxygens. So I'm not going to write out the individual steps here anymore. I feel like we are all on the same page with how we calculate the molar mass. So I'm going to do all this multiplication, and then I'm going to add these values together. Please practice that out if you haven't been doing it on your own yet, because it's definitely a skill that you're going to need to be very comfortable with. and we're going to get 180.16 grams per mole. That's our molar mass. Okay. So now each of these equalities that we're going to need for our molar mass, the equality that we can make is for every 1 mole of our glucose, it's going to be 180.16 grams. Okay, that's equality number 1. Equality number 2 is going to be Avogadro's number, which tells us that every 1 mole of our compound, we're going to have 6.02 times 10 to the 23 molecules of that compound. And our third equality is going to come from our chemical formula. And in this case, our chemical formula tells us that every 1 molecule of C6H12O6 is going to contain 6 oxygen atoms. Okay. So we have 3 steps and we have 3 equalities that we're going to use. So if we start out by writing down our 32.45 grams of C6H12O6, our first step is going to be to go from grams into moles. So we're going to put our 180.16 grams on the bottom so that our units cancel out, and our 1 mole up top. And now we've used that conversion factor, so we're good there. Our next step, we're going to go from moles into molecules. So we're going to put our mole on the bottom so that the mole unit cancels out. And then we're going to put 6.02 times 10 to the 23 molecules up top. We've used our second conversion. And then in our third step, we're going to put our 1 molecule on the bottom so that our molecule unit can cancel out. And every 1 molecule has 6 oxygen atoms in it. Okay, so we're going to do 32.45 divided by 180.16 times 6.02 times 10 to the 23 times 6. That just looks confusing because I'm going to just write oxygen. It looked like 60. Oh, man. I got lost in terms of what I had already put in the calculator. All right, so we end up with 6.51 times 10 to the 23 oxygen atoms in this example. All right. And I'd like to do one more example where we kind of go in the reverse direction. Let's look at what happens when we're given a number of atoms and we have to work backwards and figure out what that mass looks like. Okay. So for the next question, we'll still work with glucose since we did a lot of work setting up the information for the glucose. But we're going to change the question. And we're going to see that the direction of our pathway is going to change when this question changes. Okay, so the new question is going to be, how many grams of C6H12O6 contain 7.42 times 10 to the 23 oxygen atoms. All right. So in this case, they're giving us the number of atoms and they're asking us to work towards the number of grams, right? So if we're given the number of atoms, we're going to be able to relate the number of atoms that we have back to the number of molecules that we have. Okay, just like we were able to take our molecules and figure out how many specific atoms we have. Sorry, I shuffled that around. If we know how many atoms we have, we're going to be able to use this relationship and we're going to be able to figure out how many molecules specifically that we're looking at. Once we know how many molecules we have, we can use Avogadro's number to figure out how many moles that represents. And once we know how many moles we have, we can use our molar mass to figure out how many grams that is equal to. Okay. But you're going to see that we'll be able to use these same equalities. We're just going to be positioning them differently based on the information that we're given to start with. Okay. So in this question, our starting information is our 7.42 times 10 to the 23rd oxygen atoms. And our first step in this case is going to be to recognize that there are 6 oxygen atoms in every one molecule of our glucose. Okay, that's our first step. So we're going to take our number of oxygen atoms and we're going to divide it by 6. And that's going to tell us how many molecules of glucose we have. Then we're going to be able to use our relationship with Avogadro's number. And we're going to say, okay, however many molecules we have, we're going to divide that number by 6.02 times 10 to the 23. In your calculator, please keep this in parentheses. Okay, we see how we have molecule up here. So our next step, our value with molecule in it goes on the bottom so that these can cancel out. And 1 mole goes up top. Okay. And then in our last step, we're going to use our molar mass. We're going to put mole on the bottom because we want the mole and the mole to cancel out. And we're going to be putting our 180.16 grams up top. Okay, and again, because we're taking our number of oxygen atoms, we're going to divide it by 6, and that's going to tell us how many molecules we have. And we're going to take that number of molecules, and we're going to divide it by Avogadro's number, and that's going to tell us how many moles of glucose we have. Then we're going to take that mole value, and we're going to multiply it by the molar mass, and that's going to tell us how many grams we have. All right. But each of these steps we can figure out by using our equalities and then matching up unit to unit in every step to make sure that our units are always canceling out as we go. So this divided by 6. And then we're going to divide this by Avogadro's number. Again, make sure that that's in parentheses or it's going to throw your order of operations off. And then we're going to multiply it by 180.16. And we're going to end up with 37.0 grams of C6H12O6. And that's going to be our final answer there.